So this is nuclear fusion. Remember, fusion is joining nuclei, yes? So we are fusing them together. That is how we can remember this. A fission reaction creates fissures. Yes? There we have it. Okay. Fusion powers the sun, and there's something called the proton-proton cycle. Is that in your little note guide? That little thing? Nothing about fusion? Yeah, that's okay. That's okay. Just hang on to that. But the notion here is ultimately that hydrogen turns into helium. And the crazy thing about this is that it only happens, it happens naturally in the cores of stars, in the center of our sun, because if you look at it, right, these are hydrogen atoms coming together. Hydrogen is positively charged. The nuclei are positively charged. They don't want to go together, yes? Right? And so they have to be moving fast enough so that they overcome their repulsion and fuse, yes? Okay? So that requires speed. Speed is heat, correct? Yeah. Okay? They also have to be close together, because if they're far apart, they might never encounter each other. So that's why you need heat and pressure. It turns out that you also need luck for this to happen. Okay, because if you do the calculation, it turns out that the reaction rate that the sun has is way higher than what you would predict by those two factors alone. So how is it that it's happening? Well, you know, the Heisenberg uncertainty principle explains yet another thing, right? Remember that particles can have an energy that is uncertain, yes? So normally they don't have enough kinetic energy to overcome the repulsion, but every now and then they go, oh, yeah? It's kind of like, bam, yeah? Every now and then it hurts, right? You know, so these two things are uncertain, and the particles gain energy from nowhere long enough to fuse, and then that's all they have to do, right? Just kind of interesting. Helium, you can also fuse helium. You can keep going, right? So helium, you can make things like carbon. Carbon can fuse to make things like magnesium, and then really, really hot stars might even make iron and nickel and stuff. Why don't you make things heavier than iron or nickel? Because then you're losing energy. You're actually storing energy. Iron and nickel are the most inert things, right? Yeah? So there's the most tightly bound. Fission, and these things aren't created by stars. They're created by gravitational collapse of giant stars, right? Okay? So here you split these guys to release energy, and these guys, you actually fuse these guys together to make energy, right? So, you know, we killed people in Hiroshima with this reaction. And then in the 50s, we discovered, hey, there's an even better way to kill people, and that is you take hydrogen and you fuse it together, right? Now, they do that because they use a fission bomb as the fuse, right? It's like the blasting cap that sets it off. So to make a hydrogen bomb, you have to have, you surround it with a regular uranium bomb or plutonium bomb, I don't know which one they use, with hydrogen. How do you store the hydrogen safely? Well, what they use is lithium hydride. It's a solid, right? It's LiH4. Right? It's a solid, and it represents the most stable form way. It's the compound that is most by mass hydrogen, I believe, the most stable thing, right? You just surround it with lithium hydride, and there's enough hydrogen to now you're into megatons, right? The lithium not yeah, I don't think the lithium is a major agent in there, right? Binding energy, we've already talked about this. So here's the crazy thing, right? A 235 bomb is technically difficult to pull off. Iran can probably do it, right? But it's going to take a lot of doing, right? Plutonium bombs are pretty easy to make, right? Efficient? Not efficient, but we don't really care. In other words, maybe 3% of it might explode, right? Or something like that, right? But we don't care, because if you just disperse plutonium, that's also, right, a decent terrorist sort of thing to do, right? You know. This is an American nuke. This is like Trojan, 3 Mile Island, all of our plants that we built in this country. And they're designed, this is a concrete, reinforced concrete structure. So really and this stuff it's not going to make a bomb. It's not going to explode. The worst thing it can do is just melt and release, basically blast all of this radioactive water into the air. And this is what happened at 3 Mile Island, is that this center thing melted down. It boiled off that water. The water had to vent out of the structure to keep it from blowing up, right? And it released a whole lot of radioactive steam into the air. This is water inside here. There's two actual systems. This water that's in here is actually in contact with the fuel. It has actual uranium or plutonium and stuff mixed in with it, radium, all sorts of really bad stuff. Don't drink that water. It's worse than this water, Yeah? Okay. This water is circulated in here, has to be treated like toxic waste, et cetera, right? That water, because it's under pressure, is hotter than boiling. And so you use that water to boil this big tank of water. That's your boiler. Hotter than boiling because it's under pressure. I know, isn't that crazy? But under high pressure, it can be much hotter than boiling. Like a pressure cooker raises the temperature above boiling so that, yeah, right? Okay. So you boil this water. That water is clean. Don't drink it either, but it drives your steam turbine, right? And then you generate electricity. Steam turbines leak steam, and there, there we have it, right? So this is how we do it. Notice that the fuel here, this is fuel. There's some moderator. I think we use water, but there's something else. I don't know exactly sure. Moderators slow down neutrons so that they are more likely to react and cause a chain reaction. These control rods are things that just absorb neutrons. You stick them in and it just shuts the reaction down. Notice that they've implied that there's a big heavy thing so that if they need to, they can just like pull the pin and the thing goes ka-chunk and shuts it down, which it will do if the core hasn't melted. If the core melts, the rods don't go into it, and so it, you can't stick the rods in, right? Okay. In Chernobyl, what happened in Chernobyl was they're using graphite, I believe, as a moderator, carbon. Right? And most people don't know that Chernobyl was not a nuclear explosion. It was a nuclear reaction caught the graphite on fire. It was a conventional fire. It was just a big old firestorm. It was really bad because it was the stuff that was burning was that nuclear core. The core was burning, and it was strewing radium and strontium and just all this stuff that we treat as this very toxic waste. It was strewing it up into a huge firestorm cloud, right? That reached the stratosphere. It burned so hot. Right, and then that just spread over this enormous area, right? They sent firefighters in there, and they didn't say, look, we're sending you to your death. These firefighters went in. There were these ponds of water around the nuclear plant for cooling, and they put their little intake hoses into that, and they're pumping all this horrible stuff through the pumps of the thing all over themselves. They're trying to put this fire out, right? If you go into that forbidden zone with a Geiger counter, the fire trucks are just there in the field abandoned. I don't know if the people got sick or whatever, if they left them there because they were so radioactive, right? All of those people died. The trucks, as you drive by these fire trucks, they're some of the hottest things there because they're just full of that stuff. The Geiger counter just goes brrrr as you go by. They're like over there in a field a quarter mile away, right? I mean, it's just an amazingly bad thing. And the thing that was really evil about Chernobyl was that when it exploded and when the whole thing happened, the Soviets should have immediately told everybody, keep your kids indoors, keep your cows in the barn, feed them hay, right? No. They were like, nothing's going on in the evil Soviet Empire. Everything's okay. And suddenly Geiger counters and stuff are going off in like, Eastern Europe, right? Suddenly the people are going, gee, there normally isn't this much radiation, right? And so kids have been drinking milk from cows that were eating radioactive strontium, right? Strontium can bind to things that calcium binds to, so these kids are getting like cancer, that there was all this stuff going on. I mean, it didn't happen immediately, but there's definitely cases that happened because of this, right? When we talked about this to death, obviously nuclear power, France uses they gets 80% of their electricity from nuclear power. Not 80% of their power, but 80% of their electricity from nuclear power. There's obvious advantages to nuclear power. We probably have thousands of years of energy in our known reserves of uranium, especially if we go to like breeder reactors. Question?
What exactly makes you insane?
Oh, it just destroys your DNA. The actual radioactive things, the particles, either the alpha particles or whatever it is, right, do damage to your DNA, and then you don't. That's what happens. That's what cancer is, right? You're not. Basically, one of the things that controls the division process has been shut off, and then it just divides. It doesn't know to stop.
So it can be like given to you in like the air or water.
Yeah, you can ingest. The very worst thing is that you ingest it, and even ingesting an alpha source at close range, it's just sitting there bombarding your cells, right? So that's the danger. So obviously there's good things. There's nothing like nuclear power for a submarine, right? Nuclear reactors don't give off smoke. Yeah. So you've got this source. Nuclear submarines can go down. They can stay underwater for 9 months. They get their oxygen out of the ocean water because they've got electricity. You can just